All right, everyone. Today, we're going to talk about a hazard that's completely silent, totally invisible, and, well, it's catastrophically fast. We're talking about vacuum collapse. It's a phenomenon that can crush a massive steel tank in literally the blink of an eye. And understanding this isn't just some textbook exercise. It's absolutely critical for keeping our plant and ourselves safe. Think about this for a second. We spend so much of our time in training worrying about overpressure, right? We've got relief valves, strict procedures, we're all trained to fear the Big Bang. But what if the real hidden danger, the one that gives you zero warning, is the complete opposite? What happens when you take the pressure away? Because when a vessel fails under a vacuum, it doesn't just spring a leak. It doesn't bulge out, giving you time to react. No, it implodes. The failure is instantaneous. It's total. And the result looks exactly like a soda can that you've just crushed in your hand. This isn't a slow-motion failure. It's a sudden, violent event. And the contrast here is it's stark. Internal pressure, the stuff we're used to dealing with, is honestly pretty forgiving. The steel stretches, you might see a bulge, maybe you'll even get a pinhole leak. You get warning signs, you get precious time to shut things down. But external pressure from a vacuum, it offers none of that. There is absolutely no warning. Just instant, catastrophic collapse. So why does this happen? I think our first instinct is to think, well, the tank wasn't strong enough, right? The walls weren't thick enough. But that's not really the whole story. The real key here isn't about the material's strength. It's about its stability. It's about geometry. Everything, and I mean everything, boils down to this: the LD ratio. It's the ratio of the tank's unsupported length to its diameter. In vacuum design, length is the absolute killer. It's not about how thick the steel is, nearly as much as it's about how long and skinny that vessel is. The higher that LD ratio, the more unstable it becomes when the pressure's on the outside. Here's the perfect way to think about it. Imagine the cardboard tube from a roll of paper towels. Now, if you take just a short 1-inch ring of that same tube, it's incredibly strong, right? You could probably stand on it. But what about the full-length tube? You can fold that thing with your bare hands. It's the same material, the same thickness. The only thing that changed was the long, unsupported length. That length creates a natural instability. So how does this physics lesson become a real-world disaster? Well, this isn't just theory. This kind of thing happens out in the field because of common, everyday procedures that we all do. A classic example is a simple steam out for cleaning. You fill the vessel with steam. But then, as that steam cools, it condenses back into water, and its volume shrinks by a factor of, well, over 1,000 to 1. It basically disappears. If the vent on that tank is blocked or clogged or just too small to let air in fast enough, you create a powerful vacuum. And it's not the vacuum that does the damage. It's the 14.7 psi of the atmosphere all around us suddenly turning into an immense, crushing force trying to fill that void. And it's not just about steam. The exact same physics apply if you're doing a rapid pump out. If you're pulling liquid out of that tank faster than air can get back in through the vent, you are creating a vacuum. The atmosphere does not care how that empty space got there, it will try to fill it. And if that means crushing a multi-ton steel vessel, well, it will. Okay, so that's the hazard. It's serious, it's fast. But the good news is this is a solved problem. Thankfully, there is a proven and actually pretty clever engineering control to prevent this exact type of failure from ever happening. So we know the problem, right? The fundamental issue is that L/D ratio. A long, skinny tube is just naturally weak when you push on it from the outside. You just can't change that law of physics. But what if you could trick the physics? And that is exactly what stiffening rings do. By welding these simple steel rings around the outside of the tank, we basically break up one long, unstable cylinder into a whole series of short, incredibly stable ones. This design is frankly brilliant. It doesn't just add brute strength, it fundamentally changes the vessel's geometry to get rid of that instability. The L in our L/D ratio is no longer the total length of the tank. It's now just the short little distance between each ring. We're literally turning that weak paper towel tube into a stack of those super strong cardboard rings. It's an elegant, cheap, and effective solution. And that brings us to the most important part of this whole talk, our responsibility. Because those engineering controls, the stiffening rings, they were only half the battle. The other half comes down to us, to our procedures and our vigilance. Look, the engineering that goes into designing a vessel for vacuum is incredibly precise. These aren't just simple formulas you can plug into a calculator. They use these complex, iterative chart methods right out of the engineering codes. What that means for us is that we have to respect the design. We can never, ever assume a vessel can handle vacuum just because it looks big and sturdy. We have to verify it.
So here's the bottom line. This steel is just going to follow the laws of physics. It doesn't care about our production schedule. It doesn't care that we've always done it this way. It only cares about pressure and geometry. It's our job, our absolute mandate, to care about both. This is a preventable failure, 100%. But it requires us to be constantly vigilant about our procedures, especially making sure that our vents are clear, they're working, and they're sized for the job. We do not want this happening in our